Good morning. I'm going to run through two area and volume questions with you, both of which are on the top of the sheet that is in the Google Classroom. And then I'm going to leave you to do the third and fourth questions that follow these two. Then I'm going to follow up with a test after this. Not too sure what date just yet, maybe Thursday, but it'll depend on your feedback to me whether you need more help with these or whether we can go ahead and do that test and begin the next chapter. What I'm going to look at first of all is a question that comes from 2019, so last year, paper 2, question 7. A very straightforward area and volume question, but nonetheless one that involves quite a bit of formula work. So always of great help are your tables. Don't ever attempt to do anything with area and volume without your tables. So let's have a look at it. A cattle feeding trough of uniform cross-section 2.5 meters in length, okay, so there's 2.5 meters in length, is shown in figure 1. The front of the trough, segment ABC, is shown in figure 2. The front of the trough is a segment of a circle of radius 90 centimeters. The height of the trough DB is 30 centimeters. OA equals OC equals OB, which is 90 centimeters, and OB is perpendicular to AC. Now this is interesting here. OA equals OC equals OB. OA equals OC equals OB. The radii of the circle. So therefore they are all exactly the same length. So OA is 90, OB is 90, OC, but the radii, that's the key thing to keep in mind when we're dealing with this. Notice also that all measurements in figure 2 are given in centimeters. One figure here in figure 1 is given in meters. So we've got to be very careful that we do what the calculations ask. And if we need to change from centimeters to meters, we do so before we do any calculations. So part 1, find AD and give your answer in the form of A root B centimeters, where A and B is an element of Z, integers. Okay, so they're allowed to be positive and negative whole numbers. So where is AD? AD happens to be this here. Now you'll notice straight away there's a mark of a right angle, so they're drawing your attention to the fact that inside this shape there are two right angle triangles. The one I'm looking for is this one here. So we go from O to D to A. Now what do we know about that right angle triangle? Let's just take it out here and draw it. Sometimes it's better to take the shapes out and do them this way. We know that that's 90 from A to O. We also know from O to B is 90. However, here they tell us that this is 30, so therefore O to D must be 60. And they want me to work out the length of AD, which I'm going to refer to for the moment as X. Straightforward question, right angle triangle, the theorem of Pythagoras. And the theorem of Pythagoras says that the hypotenuse squared is equal to the sum of the squares on the other two sides. So that simply means 90 squared is equal to 60 squared plus our x squared, what we're looking for. 90 squared is 8,100. 60 squared is 3,600 plus x squared. So when you take them away from each other, we get 4,500, which is equal to x squared, meaning x will be the square root of 4,500. And if you have your calculators handy, the answer comes out as 30 root 5. Now I've these questions already looked at just to save time, not to be foosing around with a calculator, so I have the answers there. So that's 30 root 5. Now when you do find a measurement, remember it's going to be used in different parts of the questions. So let's move on. Part 2, find the angle DOA correct in radians, corrected 2 decimal places. Now look, radians, I don't like working with radians. I don't want you working with radians unless the question actually says so. So in this case, what I would suggest you do is you work in terms of degrees, and then we can work our way back to radians if asked to do so. Okay, and I'll show you the relationship between the two in a few moments. So find the angle DOA. Well, first of all, where is DOA? DOA is here. There it is. So let's put that in as alpha. Alpha is the symbol for the unknown angle. And what we also know is that this one here is 30 root 5. And we also know that that's 60. So again, we've got a right angle triangle. And in the right angle triangle that they're drawing our attention to, right angle here, we've got 60, we've got 90, we've got 30 root 5, and we've got an angle here, alpha. Go back to junior cert trigonometry. Whenever you have an unknown angle, all that's required to work out that angle is any two sides. So I'm going to simply take these two sides here, the 90 and the 60. And in relation to alpha, these two sides would be known as the hypotenuse and the adjacent. And the only function that uses the adjacent of the hypotenuse is the cosine, and the adjacent of the hypotenuse is 60 over 90, both of which are divisible by 30, better known as 2 over 3. So if I want to work out the angle, all I have to do is get the inverse cosine of 2 over 3, and you'll be delighted to know I have that done also. That comes out as 48.19 degrees. Now look, don't worry about radians for the moment. There is a relationship that says that pi radians is 180 degrees. So if you were asked to get this answer down into radians, you would put 48.19 below that. You would take that multiplied by pi, so it would become 48.19 times pi over 180, and you can do that on your calculator quite easy. So 48.19 multiplied by pi, and then we're going to divide that by 180, and the answer comes out as 0.841 radians, and that's the 48.19 degrees. But don't worry about that yet, we will be looking at radians later on. For the moment, we'll simply deal with degrees. Okay, so part 3, find the area of the segment ABC. Now ABC is this segment here. We referred to it at the beginning of the question. They're looking for you to get the area of that, which means taking ordinary everyday area shapes, that segment, as they call it, ABC, that is the difference between the sector here and the triangle. So therefore, if I want to work out what the segment is, I would have to first of all work out what the sector is, like this, and take away from that what the triangle is. See? And that's going to leave you with your segment ABC. Now, to get the sector, we have to know the angle up here. We've dealt with this already, because a sector is nothing more than a fraction of a circle. So that's going to be pi r squared, providing it was a full circle. But if I know this angle here, I create the fraction in front of pi r squared, which will then give me the area for the relevant sector. We already know what the angle here is. We were told earlier on that the angle there was 48.19, so that means all of that angle there is 48.19 multiplied by 2. It's twice that, which comes out as 96.38. So all of that is 96.38 degrees. So 96.38 degrees in there means now I can put 96.38 over 360, so that represents the fraction of the circle that we're dealing with, which we call a sector. Put it in front of the area formula for a circle, which is pi r squared, and take away from that the area of this triangle. Just use half the base by the perpendicular height. The easiest way to do it. Okay, so let's fill this thing in. 96.38 over 360 pi times the radius squared. Now we know what the radius is. We've got 3 of them there to deal with. One is marked for us. It's 90 squared. Okay, but notice, give your answer in meters squared. So before we work, what we should really do is turn all of these centimeters into meters. So 90 centimeters would be 0.90 meters, minus a half the base. Now, didn't we work out earlier on what AD was? If I remember correctly, AD was 30 root 5. So that means AC is going to be 60 root 5. It's just twice that. And what's the perpendicular height? Well, the perpendicular height, OD, is OB minus the 30, which is 60. Now again, they're in centimeters, so we've got to use them in terms of meters, because the answer is to be in meters squared. So the base is nothing more than that divided by 100. That's 0.6 root 5, multiplied by the perpendicular height in meters, 0.6. And again, there's nothing more there than calculator work. So when we work that out, we will end up with, on your calculator, 0.28 meters squared. And you can just tap that into your calculator exactly as it is, and the answer of 0.28 meters squared will come out. Okay, so the last one then is find the volume of the trough and give your answer in meters cubed. Now again, keep in mind that the trough is now a prism, and we had that word before. A prism is nothing more than a face which has a 2D face multiplied by the length. Okay, so writing on my own face. So it's I'll do that again. Erase that. Sorry. So therefore, a prism is equal to a 2D face which will be obviously this one here, we already know the area of that, multiplied by its length, okay, which will be this one here. We know what the area of that is in meters squared, because I already worked that out as being 0.28 meters squared. So that means it's 0.28 meters squared multiplied by the 2.5 meters that we've got in length for this particular trough. So 0.28 multiplied by 2.5 will give me a volume of 0.7 meters cubed. Okay, and that's it. That's that question. That's how easy that question was. Totally dependent on formulas, a little bit of trigonometry thrown in there, but nothing over junior cert honours trigonometry. The sine rule. We should all be able to remember what the sine rule is. Okay, let's do one more question. And let's take the bottom of this one. A sand timer for games is shown in the diagram. Each half of the timer consists of a hemisphere, a cylinder of height 3.5 centimeters, and a cone of height 1.5 centimeters. All of the parts have a radius of 1.25 centimeters. The upper half of the timer is full of sand. Find the volume of sand in the upper half of the timer and give your answer in centimeters cubed, correct to 2 decimal places. Now look, there's a number of things here you've got to be careful with. First of all, you give your answer in centimeters cubed to 2 decimal places. What do we ask for? Volume. So once you've got those key ideas in your head, it's just a matter of working out, well, what are the basic shapes in this irregular shape? So all of that together would be irregular. But what's it made of? Well, it's made of a hemisphere. Like that. Okay. It's also made of a cylinder. So the little hemisphere sits on top of a cylinder. Like that. And at the bottom of that, we've got a cone, which sits at the very bottom of the cylinder. So therefore, if we were to work out what the volume of all of this is, break it open. Hemisphere, cylinder, cone. And all you've got to do is write down the respective formulas. This is a hemisphere, so it's going to be half of 4 over 3 pi r cubed, which is 2 over 3 pi r cubed, plus the volume of a cylinder is pi r squared h, plus a cone, a third pi r squared h. Now, the lovely thing here is that the radius is all the same. So it's 1.25 there, it's 1.25 there, and it's 1.25 there. The height of the cylinder, we're told, is 3.5. They're very generous. And then we're told also that the height of the cone is 1.5. So it's a very simple matter of filling these things in. 2 over 3 pi by 1.25 cubed plus pi times 1.25 squared times 3.5 plus a third pi by 1.25 squared by 1.5. Now again, just write them in, substitute into the formulas, get the calculator to do the rest. Because if you do that properly, and I have the answer here already, if you tap that into your calculators, you'll get an answer of 23.73 centimeters cubed to 2 decimal places. So again, very straightforward. Break up the irregular shape into 3 regular shapes, and then use the appropriate formulas and work out the total volume. Sand flows from the top half of the timer to the bottom part. As it flows, the top surfaces in both parts remain level. At a certain time, 98% of the sand has flowed into the bottom part of the timer, and they want you to find h, the height of the remaining sand. So in other words, they want you to get h here, right, which has kind of been exaggerated over here, in the conical part at the top of the timer, and give your answer in centimeters, correct to 2 decimal places. Okay, first of all, again, let's highlight some relevant material here. 98%, I want to highlight here, 98% of the sand has flowed into the bottom half. What's my immediate answer to that? My immediate answer to that is, oh, well then this part here must be the remaining 2% of the volume that we discovered in the first part. And that volume, as I told you already, was 23.73 centimeters cubed. So in other words, this cone here is only 2% of the original volume. And 2% of the original volume, if we work that out, 23.73 multiplied by 0.02, because 0.02, that's a symbol by the way, so it's 0.02 multiplied by 23.73, and that works out as 0.5 0.4746 centimeters cubed. So now I know that the volume of that cone is equal to 0.4746 centimeters cubed. And the cone I'm talking about is the cone that's made by the remaining sand. Okay, now write in the appropriate formula. A third pi r squared h equals 0.4746. Do you see the problem? The problem is we have two variables. You cannot solve an algebraic equation with two variables. So why do they give me this diagram here? This diagram is a diagram to allow you to try to manipulate a formula that will get you h in terms of r, or more importantly probably r in terms of h, because we're looking for the height. So therefore let's just take a look at this. Let's see what this is trying to tell us. And again, something from your junior cert, if you remember back, there was this idea of similar triangles. So if you just take what's in this part of the diagram here, we have 1.25, and here we have 1.5. See that? So 1.25 at its widest, 1.5 at its highest. Then the remaining bit of sand is R and H. Now, if I was to take those as two triangles, the large one and the small one, and give them each their respective numbers and letters, 1.5, and then here R and H, immediately what you can see is that the ratio between these two would be the same as the ratio between these two. So we get a lovely fraction. We get 1.25 is to R as 1.5 is to H. So in other words, the relationship between these two would be the same as the relationship between these two. And when I talk about a relationship, I talk about a ratio. When I talk about a ratio, I talk about a fraction. Okay, so the fraction that these two make will be the same as the fraction that those two make. So what do I want to get? R in terms of H, because it's H is what we're looking for. So therefore a quick multiplication across will give you 1.5 R, if you do a cross multiplication, is 1.25 H, which means R is equal to 1.25 H over 1.5, which means now in this formula I can replace R with 1.25 H over 1.5. So let's see what that's going to do for me. 1.25 H over 1.5 to be squared times H equals 0.4746. Do you notice? It's all in terms of H. We can now solve this thing. So when we square 1.25 H over 1.5, let's do that on the calculators, we'll end up with 25 over 36. And the calculator will tell you this. It'll be 25 over 36 H squared. So square the 1.25, square the 1.5, you'll get 36 over 25. Sorry, the other way around. Apologies. It'll be 25 over 36. Let me do that again. Okay, so you'll get 25 over 36 H squared times H equals 0.4746. Now, that will give me then, I have this done out, so I'm going to do it very quickly. I can find it here. Yeah, so we can multiply this out. We get 25 over, so maybe I just 25 over 3 36s. And that's going to be 108. Pi H cubed equals 0.4746. Now, to take this, we want to get H cubed. What's going to happen? It's going to be 0.4746 multiplied by 108 divided by 25 and divided by pi. So that will give me, if I work all that out, that will give me H value, I'm sorry for squashing this in down here, of 0.8673. And that will be centimeters. So in other words, if we want to go from H cubed, which is all this here, that means H would be the cubed root of that. And again, I told you before, manipulate before you calculate. So in other words, do all the manipulations that you need to do, and then at the very end, when you've got your fraction built, you're going to take the cubed root of this fraction here. So you're going to get the cubed root of this thing, and you're going to get the cubed root of this, which will give me the answer as the height of 0.8673 centimeters. Okay, now that question, quite a straightforward question, quite an easy question. The next one, which is 2017 paper 2 question 7, again I'm going to run through this with you, and just to show you how these questions, whilst they are a little bit thought-provoking, are actually quite similar in the way in which we work them out. Okay, and again I have my trusted answers done out already, so that I don't have to be going rooting for a calculator. Two solid cones, each of radius r and height r. Good, so they're all the same letter. That means they're the same. Once you use the same letter, they have exactly the same value. Are welded together at their vertices and placed in the smallest possible hollow cylinder, as shown in figure 1 below. Okay, so figure 1. Show that the capacity volume of the empty space in the cylinder is equal to the capacity of the empty space, the empty sphere of radius r. So this here, the volume of all this place here, and the volume of that, we want to show that that volume is equal to the empty space of this one. Now, how do we do that? Well, first of all, what is the empty space? How do I get the empty space in this part, figure 1? Isn't it a cylinder minus 2 cones? Isn't that exactly what it is? That's what the empty space would be. So it would be a third pi r squared h minus 2 times a third pi r squared h. Sorry, I shouldn't be a third there. So take that out. That's cylinder is a full pi r squared, of course. Okay, so pi r squared h minus 2 cones, which is a third pi r squared h. Now, first of all, what is the radius? It's r. What is the height? So don't forget, the height we're told already is 2r. And here, the radius of that is r. And I want to prove that when I do that, all of that is equal to 4 over 3 pi r cubed. So, pi r squared h, let's take it down here. It's pi by the radius squared, which is large r to be squared, by the height, which is 2 times large r, minus 2/3 pi by r squared again, which is big R to be squared, by the height, which in this one here, we can see, is also r. See that from the diagram? Okay. What does that give me? That gives me 2 pi r cubed is equal to, or minus, 2 over 3 pi r cubed. So again, let me take out that. It should be minus. I'll take away. Okay, so minus that. And 2 pi r cubed minus 2 over 3 pi r cubed. Don't forget, that's 6 over 3. So that's 6 over 3, just to get the fractions the same to show you. It's 2 over 3 pi r cubed gives 4 over 3 pi r cubed, which is exactly the same as what we have up there. So that works fine. Okay, so nice little play around with the formulas, and you can see how important the formulas are, how important your tables are going to be. Part B. In the remainder of this question, r is 12. Okay, so that means we now have a cylinder radius 12 and a total height, don't forget that, of 24. So keep that in mind. Water is poured into both the cylinder and the sphere to a depth of 6 centimeters as shown. Find AB, which is the radius of the circular surface in the water, this one here, and give your answer in the form of a root b. Bit of a hint, a root b. We're going to be introducing square roots. Just take a look, there's kind of also a hint here. If I was to put a line down there, I'd have a right angled triangle. Doesn't the theorem of Pythagoras contain squares? And doesn't solving the theorem of Pythagoras introduce roots? So maybe that's the link between the two. So let's just take a look at that. We also know that the radius here, they're both radii, so the radius is 12. If that's 6, that's going to be 6. And if that's 6 and that's 12, well then the theorem of Pythagoras will allow me to find AB. So let's just take it out. What do we get? 6, 12, and x between a and b. So I'm simply going to use the theorem of Pythagoras to work out this length of AB, which is 12 squared is equal to 6 squared plus x squared. 144 minus 36, because you take that over here, is equal to x squared. That's going to give me, if I can find it, 108. is equal to x squared. So when I get the square root of both sides, x will be equal to the square root of 108, which your calculator will tell you is 6 root 3. Now just check, it is in the form of a root b, and both a and b are elements of natural numbers. Yeah, so that answer is perfectly acceptable. Okay. Part 2. Find CD, the radius of the cone at water level as shown in figure 3. Okay, now I just want to draw your attention to something. There, to there, to there, to there. Do you notice that's something similar to the previous question where we had a little triangle inside a bigger one? That means that there's going to be similar triangles used here. So let's just think about that for a moment. This one is the radius of the large cylinder, which is 12. And this here is the height of the cone, which is 6. Okay, now we're told that this is 6 here, so that's another 6 up there. So the whole thing from there to there is 12. Let me just make that a little easier to see. I'll just take out that 6 for a minute, and let me just write in what it is. Okay, so the whole thing, so from there to there is 12. The height of the cone is 12. Okay, now we're told that water is to a depth of 6. You see that? Inside. So the water is up to a depth of 6, even though the entire cone has a height of 12. So if the radius to the height is 12 to 12 in this triangle, then if we separate the two, look, 12 is to 12 in the large one. What about the small one? Well, in the small one, 6 must be to 6 because the ratios have to be the same. They are similar triangles. They both contain a right angle. So if the large one is 12 to 12, and we know that this here is 6, and that's going to be 6 there, well then obviously 6 to 6 in the smaller triangle gives us the same ratio, which means that CD happens to be 6. Really no maths, it's just a comparison of the two similar triangles that are in that question. So now we know that CD is 6. Part 3. Verify that the area of the surface of the water in the sphere is equal to the area of the surface of the water in the cylinder. Okay, so this here, so all that on the top there is equal to this. Can you see it? There. Now, what that means is that I want to prove that the circle that is present here with radius AB, didn't we work out AB already? AB happens to be 6 root 3, yeah, is equal to this region between the two discs. So in other words, it's going to be that circle minus the inner one. Apologies for the diagrams. So what did we say the large radius was? We said that the large radius was 12, and we said that the small radius there just a minute ago was 6. So all I want to do now is to show that the area of that circle is the same as the area of the big one here minus the area of the small one. So what have we got? Area pi r squared equals this one here, the large circle first, pi r squared, which is 12 squared, minus pi small one, 6 squared. So I want to see that pi times 6 root 3 squared is equal to pi by 12 squared minus pi by 6 squared. Okay, let's have a look. Pi times 6 root 3 to be squared. Now 6 root 3 to be squared is 108 as far as I know. Yeah, 108, got that in the previous part. So 6 root 3 squared is 108. Pi should be equal to 144 pi minus 36 pi. Can't argue with that. 108 pi is equal to 108 pi. So it works. So it is. Okay, and lastly then, the mathematician Cavalieri, obviously Italian, hope he didn't live in Lombardy, wouldn't be alive today if he was. The mathematician Cavalieri discovered that at the same depth, the volume of water in the available space in the cylinder is equal to the volume of water in the sphere. Use this discovery to find the volume of water in the sphere when the depth is 6 centimeters. And give your answer in terms of pi. Now, it says, his discovery told us that if the depth is the same, then the volume will be the same. So they want me to work out the volume that's at the base of this particular sphere. There's no formula in your tables that will allow you to work with that type of a shape. But there is a formula and formulas that will allow me to work with the shape of the water over here. Because at the end of the day, and I need you to think about this, look at the diagram, that volume of water is nothing more than a cylinder with a height of 6. So we're just dealing with this part down here, just here. Okay, let me just do that. We're just dealing with this part. So a height of 6 and a radius of 12. But what's in there is one of these shapes, most unusual. It's like these things that the elephants stand on in the circus. So remember those yokes? The elephants would put their paws on them, or one paw or whatever, and lift them up. Bit like that, bit like a stand. But I hope you can see what I'm trying to do with this. This sphere here, or this cylinder here, minus this, what we would call a frustrum of a cone, a bottom part of a cone. It's like a cone with a top that's cut off. Now in your tables, and I just need to show you this, in your tables on page 11, I don't know whether you can see that or not, there's a formula for the frustrum of a cone. And I'm going to write it out. So this one here is nothing more than pi r squared h minus the frustrum. Now, if you look in here, we've got the volume, which is 1 over 3 pi h times r squared plus r plus r. Now, r squared means the big radius down here, which we know already is 12. Then it's the little radius up there that we know is 6. And the height between the two we're already told is the same as this one here, which is 6. So it all fits. So a pi times 12 squared times 6 minus a third times pi times the height, 6, times, now, r squared, 144. 12 times 6, 72. So let's just do that very quickly over here. So we've got 144. So that's 12 squared. 12 sixes, 72. And then r squared down the bottom, isn't it? R squared, yeah, which is 36. Now, if I add all those together, 144, I'll get, so 144 plus 72 plus 36 comes out as 252. Okay, so let's do this very quickly over here. Pi by 12 squared by 6. So 12 squared, 144 times 6. That comes out as 864 pi minus a third times pi times 6 times 252 comes out as 504 pi. So therefore, the volume of water left around this frustrum in this cylinder will be, that's not right, 12 squared by 6, 12 squared by, apologies, 12 squared by 6, yeah, will be 504. Whoops. So 864 minus 504, that will become 864 minus 504, that comes out as 360 pi centimeters cubed. And that water volume there will be exactly the same as the volume of water that will be down here. So again, the volume of water, that's what Cavalieri said, the volume of water here around this frustrum of a cone inside the cylinder will be exactly the same as the volume of water at the bottom of the sphere, providing their heights are the same. There is no formula for that. Forget it. No formula in the tables for that whatsoever. But there is a formula for cylinder minus frustrum. And that's why we've got to engage with that formula there. Okay. So that finishes that question. And I'm going to leave you now with the questions that are on the worksheet. You'll find them in Google Classroom, and I'll put up the details of what questions I want you to do, and if you have difficulties with any of them, come back to me by email and I'll give you the solutions.